Great. So yeah, thanks to Mathis for the introduction. Thanks to Gregor for inviting me. And yeah, as Mathis said, I have been a PhD student in Bochum until 2015. Worked primarily with dynamic neural fields there. And now I'm still doing computational modeling of behavioral data in kind of a similar field. Typically not directly working with dynamic neural field models, but still with kind of related or compatible concepts. And also doing behavioral testing, so testing people on their working memory performance and working memory behavior. And using that to some extent also to test or confirm predictions from the dynamic neural field models or kind of phenomena that we would expect from these models. And today I'm going to talk about one example of such a project, which addresses drift in your population activity as a cause for a deterioration of working memory over time. As you probably know by now, working memory or visual working memory is a relatively detailed but strictly capacity limited storage system that acts over short durations, typically on the order of a few seconds. And this capacity limits have been investigated in quite some detail and have been the focus of many studies. Typically described in terms of the effects of set size. So in this kind of simple example task here, participants would have to memorize these four colors and their locations on the screen. And there's a brief delay where they have to keep that in memory. And then they are tested, for example, by showing one of the colors, and people have to click on the screen where that color appeared. And you can test these capacity limits by varying the number of items, or sort of color disks here, described as the set size. And there are then pretty dramatic effects. If you increase the set size too much, then the memory performance will drop substantially. And there have been competing accounts based either on fixed slots for working memory items or some continuous memory resource. And of course, the dynamic neural field theory itself also provides one account that is kind of intermediate between fixed memory slots, in that it has fixed memory states in terms of stable activation peaks, but also a kind of continuous memory resource underlying that in the total neural activity in a neural field. What has been somewhat less studied are effects of delay duration. It's quite intuitive that the longer you have to hold something in memory, the worse your recall performance is going to be. But the effects of that are actually rather subtle. And the phenomenon is less well studied, less well understood. And there are only a few quantitative models of delay effects. We're trying to explain delay effects based on this concept of population coding, which I think you're all familiar with by now. So if I want to represent, for example, the location of an item in space, in visual space, a simple scenario where the item is always somewhere on a circle around the center, I can have a population of neurons with different tuning curves that all respond to some extent to different locations on the circle, and have a preferred location at which the neurons will fire most strongly, and other locations at which they will fire less or not at all. And in the type of model that we're using in Cambridge now, we assume that, well, a stimulus like a location here in this example is encoded in this neural population by the firing rates of neurons. And we kind of take just a snapshot of the neural activation. So over a short period of time, we just count how many spikes each neuron is producing. We assume that the spikes are generated by a stochastic process, so a Poisson process that is based on the firing rate that is determined by the neural tuning curve, but has some random factors in there. So the number of actual spikes generated will vary from trial to trial, even if you have the same stimulus. And so we don't really consider here these whole dynamics of how activity is retained in the neural activation, but really just assume that at the time when the stimulus is presented, it is encoded in neural activity. This activity remains there for a while during the delay duration, and then you can read out the information by trying to decode from this neural activity in the form of spike counts. And you can perform this decoding as a maximum likelihood estimate. So you just try out what is the possible stimulus location that is most likely to have produced this pattern of spiking activity, which will be somewhere close to the true stimulus location, but due to the stochasticity in the firing, not measured exactly. And if you assume that the response or the kind of the recall in a memory task is produced based on this decoding, a certain distribution of responses or of response errors around the true stimulus feature, which in this example may look something like this. The advantage of this kind of model over dynamic models is that it's far simpler. So this model here really has only two free parameters: the width of the tuning curves and the mean total number of spikes that is produced. And based on that, you can analytically determine what the response distribution should look like if you perform this decoding from neural activity. The disadvantage, of course, is that you ignore all these processes that underlie both the encoding and maintenance in working memory and the reading out and creating a response from that. So it's really a very simplified model, but therefore analytically much more tractable. This model also can account very nicely for the set size effects that I talked about in the very beginning, based simply on the assumption that total activity in the population is normalized. And if you have multiple items to memorize, then it's distributed among these items. So each item, for example, at a set size 2, will only on average produce half the number of spikes, produce that number of spikes in the population as the item would produce if it was in the memory alone by itself. And again, you can perform this decoding for these different mean number of spikes for each item. And you then get kind of response distributions or error distributions, something like this. And this actually very nicely explains human performance in such tasks. I probably should have put a figure of real behavioral data here, but you just have to believe me that the actual effects in human behavior that you see if you vary set size can be measured very closely by these kind of response distributions based on decoding from populations with a fixed total number of spikes. Now, what we're going to want to look at in this project is not the set size effect, but the effects of delay duration. And for that, we considered what mechanisms in this neural population could account for deteriorating performance with longer delays. One simple explanation is that there's a decay of activity. So over time, the activity in the neural population just becomes weaker, which is kind of equivalent then to the set size effect that there's going to be fewer spikes in the neural population that are available for decoding, and therefore decoding accuracy will decrease. Alternatively, there may be random drift in this activity. That is what you see in dynamic neural fields, where the kind of the amount of activity or the shape of this activation peak that you have there remains more or less the same. But over time, due to random noise, this activation can drift. So it's kind of its exact location in feature space can move in one direction or the other, because it is stabilized against decay and or kind of explosion of activity by the lateral interactions. But there can be an accumulation of noise resulting in the peak slowly moving in a random direction over time. So the question is, how can we distinguish between these two neural mechanisms based on behavioral data if we don't have directly put electrodes into the brain to measure the activity, which is a bit hard to do in humans. And you can't really tell it from kind of performance or error magnitude alone, because both approaches can explain pretty much any kind of error you may find. So we took, in addition to that, response latencies into consideration. We're using a task with a saccadic eye movement as a response, which I'll explain in detail in a moment. It's basically the task, the very simple task I had in the very beginning. You just have to select the location where some color was shown. And based on many previous models of this kind of task or of eye movement initiation, we assume that there's an integration of neural activity to a threshold. And once that threshold is reached, a response, so in this case an eye movement, is initiated. So that is shown here with a plot over time and the spike count. So over time, this population will just generate spikes, and the spike count will grow over time. So you just really integrate up the spikes that you have seen. And at some point, you reach the threshold, and you assume that that is then the time at which the eye movement is generated based on those spikes, on the kind of spatial information from the spikes that you have seen so far. And this produces, again, due to random noise in the spikes, these kind of response profiles, or profiles over response latencies, which generally also fit very nicely to behavioral data. And if you, for example, in this experiment, if you have kind of a lower spike rate for a single item, the integration will be slower. You have a kind of less steep slope in this growth of activity, and therefore response times will become longer, and also variance in response times will increase. So that's the idea, that we measure both response time, both response error and response latency, and then we can make predictions based on these two different accounts of delay effects, either decay of activity or random drift. And we can describe these predictions in a plot of the response standard deviation as a measure of response error or response precision and response latency. First of all, independent of this model we assume for the delay effects, we assume certain effects of set size. If you have a single item, you have high activity for that in the population, so you can relatively quickly integrate to that threshold, so you have kind of fast responses. And you also have a lot of spikes to decode from, so you have a low error or a low standard deviation. If you have two items, each of them only has half the number of spikes to decode from, the integration to the threshold takes longer, and you always have a higher error. And the same if you then increase the set size to 4, you get even longer integration times, so slower reactions and larger recall error. Now, if we take that first hypothesis about delay effects that says that activity simply decreases over time. And if that happens, then this activation distribution, or the kind of this spike pattern for the set size of 1 becomes more similar to this spike pattern for the set size of 2, because in both cases you just have fewer spikes to decode from. So likewise, these combinations of response latency and response standard deviation should simply move towards that set size 2 point, and maybe reach it and go beyond it, or maybe remain somewhere before that, based on how far the activity would decrease over time. And the same thing happens, of course, at the other set sizes. As the set size 2 delay increases, this activity would decrease and become more similar to the set size 4 profile. And so you should also see kind of behavioral measures more similar to the ones you see at set size 4. In contrast, if we assume that there's drift in the population activity rather than decay, we start with the same assumptions about the set size effects. But now this peak simply moving around doesn't change the total spiking activity, so it shouldn't have any effect on response latencies, because the shifted peak will still produce the same kind of activity, so the same increase or integration of spikes to a threshold, and response latency should therefore not be affected by this peak drifting, and should remain relatively constant over different memory delay periods. And exactly the same should happen for set sizes 2 and 4. Now, I'm going to show, or going to explain the actual experimental design in a bit more detail. As I said, it's pretty much the one I explained already in the beginning. You simply have a display of a number of colored disks on the screen that's there for 2 seconds. You have enough time to memorize them. They all have the same distance from the center, so they are kind of on an imaginary circle around the center. And you have to memorize their colors and their locations. Then there's a brief mask, so you don't have kind of an after image of those. And then there's a variable delay, over which you have to hold this information in memory. And then a cue is given in the form of one of the colors that was in the original display presented at the center. And subjects are instructed to make an eye movement to the location on this imaginary circle where they remember the color was in the beginning. We measure the eye movements with an eye tracker, so we can exactly record where people are moving their gaze. And people are doing that quite well. So we actually show now this circle here, so people know how far they have to make an eye movement. But it's actually quite intuitive to just look at the location where you think the item was originally. And in this behavioral task, we vary the set sizes. So we have 1, 2, or 4 items to remember. And we vary the delay duration. So there's either a delay here of 0.5 seconds, 1 second, 2 seconds, or 4 seconds. And we get 2 measures out of that, the response latency, which we measure as the onset of this cyclic eye movement that the participant makes to make the response. And the response location gives us a measure of memory precision. So how closely they land with the eye movement to the original location is then a measure of how precisely they memorize that location. We do one more step because in this kind of experiment, participants will sometimes simply look at one of the locations that was there, but that's the wrong item. And that would produce a very large error, but not the kind of error we're interested in. So we apply this kind of mixture model, which is a purely descriptive model of response behaviors to distinguish between responses to the target, to the angular position of the target item, and some responses that happen to the locations of non-target items, or just purely random responses that may happen if the subject really didn't pay any attention. And that precision measure that we're then interested in is this standard deviation of responses around the target item. And applying this model, we can estimate how many responses are made to the target, and that's the vast majority, 97% of all responses, and still 93% of set size 4. And only those responses that are directed to the target are the ones we take into account then later for the analysis. And we didn't find any significant effects of delay duration on these mixture of proportions. So we can assume that that whole approach is valid. So the effects are not only because there are more responses to non-target items, but there's really a change in the standard deviation of those target responses. Now looking at those results, first the effect of set size and delay duration here on the x-axis on the standard deviation, so on memory precision. And we see what we expect from many previous experiments, a pretty robust effect of set size. So the standard deviation increases as you increase the set size, so as you have to remember more and more items. And there's also a weaker but still pretty robust effect of the delay duration. So standard deviation also increases at each set size as the delay is becoming longer and longer. Note, as I said, that these effects are relatively subtle. So the y-axis here doesn't start at 0, but only shows a certain section of standard deviations. So it's not a huge effect, but it's still very robust. Now, if we look at the response latencies, we still see a clear effect of set size. So people make their response to their saccadic eye movements faster if there's only 1 or 2 items to memorize than if there are 4 items. And this effect of set size is again very robust, but there's no significant effect of delay duration. So people make their response as fast or even faster with longer delays as a kind of the response time after the cue is presented, no matter how long the delay duration was. For set size 1, that is actually not entirely a reliable measure of that, because their subjects really can completely plan the eye movement that they're going to make. But still at set size 2 and 4, we also don't see any effect of delay duration, which is consistent with the prediction of the drift model, as I will show more clearly now in this plot, as I've shown before, plotting the response latency against response standard deviation at the different conditions. We see the effect of set size is kind of what we would expect, that you get both slower and less precise with increasing set size, as assumed in both models. But then if you plot the different delay durations, you see that there's no trend really for these, for example, set size 1 results to move towards the set size 2 results. The data points are a bit noisy, of course, in the behavioral data, but they are overall very consistent with the prediction of the drift model, that you just see an increase in the standard deviation and no increase in response latency for longer delays. So this, just based on the behavioral data, that qualitatively matches nicely our predictions from this model with drift and doesn't match the predictions of the decay model. Now we went a little further and actually modeled the data with this simple population coding model. And there's still kind of one little trick there that we need to explain the data that I kind of went over before. So if we do this integration of spikes over time, so this is the plot as I've shown before, that we just count the spikes, and when I've gotten enough spikes after the queue was presented, I initiate the movements. Each spike is basically produced in its population, so each spike with little boxes here also produces or provides spatial information. And the idea is then you use these spikes that you have seen until the threshold was reached to decode the location where the item was. And based on that, you can get then this response distribution with a certain error that becomes smaller the more spikes you have. Now, if we have a fixed threshold set size 2, as I said, and as is produced by the model, of course, it takes a little longer here to get the same number of spikes. So here the 10 spikes, I think the threshold here, just a simple example that's reached here, takes twice as long as in the previous example, as in the set size 1. But of course, in the end, you still end up with 10 spikes because that's how long you wait. So this would predict the same response distribution at all set sizes, which is not what we see neither in this experiment nor in many previous experiments. So there has to be something happening that also decreases recall precision with delay. And one simple thing we can assume to model that is that spikes are kind of lost over time as well, because also during this integration to the threshold, you have to kind of hold on to the memory of the location that you're now trying to read out. And there can be all sorts of noise in the neural system that performs those computations. And there are different forms of noise that could explain it, that you just have additional spikes that aren't based on your memory. They're just a random activity, as you have also in neural fields. But this kind of approach that we assume that each spike simply can get lost with a fixed rate or with a fixed probability over time is again very nice to find analytical solutions, because it's relatively tractable to determine then how many spikes are going to be lost at different response delays. So that's the approach that we choose. So there's simply a fixed probability over time that each spike is going to be lost. If you can integrate very quickly to a threshold, then you will lose very few of the spikes that contributed there. If you have to wait longer for spikes, then many of the older spikes will be lost already when you try to make your response, and that then yields the wider response distribution, so larger average errors in this model. So this whole thing is independent of these two mechanisms of decay or drift. Those two mechanisms would simply be added on top of this basic model, that we assume that in the decay, this overall firing rate is simply lower if you have waited longer. And for the drift, we assume that this has simply shifted randomly over time. And we can then fit that is then just 3 field parameters in the model to the behavioral data. We can really do this kind of maximum likelihood fit, so we find the parameters that best explain the data. And for the decay model, for which we've already seen that it doesn't really qualitatively match the data, the best thing it can do is basically assume that there's no decay at all and fit all the different delay durations in the same way. So all the model fits that are now the color tiers are pretty much on top of each other for each set size. And it doesn't capture this kind of change in response distribution or in response error over time. Whereas the drift model doesn't capture all of it. So, I mean, since the data is quite noisy, it can only approximate the data, but it captures very nicely the general trends. And in a formal model comparison, this one provides much better fits than the decay model. It also can explain, so this model, like the dynamic neural fields models could, it not only produces these kind of summary statistics of mean response times and latencies, but can predict actual distributions of response latencies and response errors. And it fits those also very nicely to the behavioral data. So here are these distributions of response errors at different delays and for different set sizes, which are basically at all set sizes and all delay durations matched very closely. and the latency distributions, so the distributions of response times, are just combined over all delays, because the model doesn't assume that there is any change in delay duration, and this doesn't fit exactly. So there's still some aspects in the data that aren't exactly matched, but it's still a very close approximation. So that confirms to us that this kind of model can really explain the data, and that there's a drift in population coding over time, as the dynamic neural field model assumes. And there doesn't seem to be any evidence for a decay of activity over time. So that's basically the conclusion I've already given now. We tested these two possible mechanisms of delay effects, and we found that recall precision decreases over time, but response latency does not. And that is consistent with the drift model, but not the decay in neural activity. There's one more small point I want to make. The drift alone still does not explain completely the response errors that we see, because it even at the earliest delays, you already got response distributions or response errors that are kind of on the same order of magnitude as in the longest delay. So it can't really be that there's only drift as basis for these errors. And we've also seen that now in more recent studies where we look at even shorter memory delay times. So that's something that I think we can't at least immediately explain with dynamic neural fields, where this error that's basically at zero delay comes from. So delay, well, the drift over delays contributes definitely to the errors, but there appears to be something else as well that limits your response precision even at the earliest time. And it also doesn't depend only on the saccadic eye movements that you're making here as a response, because we see the same thing in experiments that allow you as much time as you want to adjust something to a memorized value. So yeah, that just as a brief point at the end. Thank you for your attention. The work was done with my supervisor, Paul Bass, at the Bass Lab in Cambridge, and supported by the Wellcome Trust.